Hello there, and welcome back. Tonight we begin a journey across time, not through the ages of kings and empires, nor among the stars, but along the ever-moving skin of our own planet. You may not feel it, but beneath the surface, the very ground we stand on is in constant motion, drifting, colliding, rising, and sinking ever so slowly. It is a motion too gradual for our eyes, yet mighty enough to split oceans, raise mountains, and shape the course of life itself. As you settle in and let the quiet of the evening surround you, imagine yourself floating far above the earth. Down below, the land appears calm, unchanging. But as we begin to turn the clock back, not by centuries, but by hundreds of millions of years, you'll see something astonishing unfold. Let us begin where the story of shifting lands first takes root. You hover silently in the sky above Earth, but this is no familiar world. It's more than 300 million years ago, a time before the continents we know had names, before the oceans held the shapes they do today, and long before human beings ever walked the Earth. Beneath you lies a vast unified landmass, a supercontinent called Pangaea. It stretches from one pole nearly to the other, encircled by a global ocean known as Pangaea. There are no modern cities, no forests of pine or oak, no grasslands, but you see swamps and fern-filled wetlands and giant insects gliding through the humid air. The land feels heavy with heat and moisture. Strange cries of primitive reptiles echo faintly across the marshes. The world is still young, yet ancient. As you drift closer, the edges of the continent shimmer with tension. Deep under the crust, immense forces are at work. The surface of the Earth, its crust, is not one single unbroken shell, but a puzzle of massive pieces, called tectonic plates. These plates are rigid, yet they float atop the semi-fluid rock layer beneath them, known as the mantle. This slow churning motion of heat and molten rock, known as mantle convection, is the engine that powers the continent's drift. But this wasn't always understood. For much of human history, people believed the continents were fixed in place, eternal and unmoving. After all, mountains do not walk, oceans do not shift, and coastlines seem solid and sure. Yet, deep beneath the illusion of stillness, the world has been dancing to a rhythm so slow that only time itself reveals it. Back in the time of Pangaea, strange patterns already began to emerge. Volcanoes flicker to life near the seams where plates meet. Earthquakes ripple silently beneath the soil. And in some places, the land begins to stretch, forming long cracks, rifts, that may one day split entire continents apart. You float gently over what will one day be Africa. Beneath you, the land is steady. But just beneath that calm lies a boundary, the faint outline of a future fracture. The Earth here is quietly preparing for change, though it will take tens of millions of years for the signs to show on the surface. Time fast forwards, and as the millennia pass, slow-motion ripples begin to roll across the supercontinent. Pangaea, once whole, begins to stretch. First, tiny movements, then larger. Water begins to seep into the growing cracks. Small seas form. What was once united is starting to come undone. The sound of wind picks up as you glide over the land. You hear the distant rumble of tectonic motion, not loud but constant, like the breath of the planet. Pangaea is being pulled apart by the very forces that brought it together. The mantle currents deep below, shifting directions, dragging the plates above them slowly outward. From space, you begin to notice subtle changes. The outline of the continent is no longer smooth. Gashes form along the edges. The supercontinent starts to bulge in some places and sink in others. Rivers change course, shorelines shift. You begin to recognize the earliest hints of the continents we know today. A faint curve that may one day be South America, a jagged edge that will become India. Life on Earth feels these changes too. As Pangaea stretches and fractures, the climate begins to shift. Some places grow hotter, others cooler. Rain patterns change. Species begin to adapt, migrate, or vanish. The geography of Earth is not just a backdrop. It shapes everything that lives upon it. But why do the plates move at all? As you drift deeper, passing through the rocky crust into the layers below, you feel the immense heat rising from the core. The Earth's core, made of molten iron and nickel, burns with leftover heat from the planet's formation. This heat rises through the mantle, creating convection currents, slow, rolling motions of rock that move like the swirling steam in a pot of boiling water. These currents are invisible from the surface, but they are what drive the mighty plates above. Imagine an immense conveyor belt, miles thick, moving continents like leaves on a river. That is the power of Earth's interior. It moves slowly, only a few centimeters per year. But over millions of years, this movement reshapes the face of the world. You rise again above the surface. Pangaea now looks more strained, cracked, and unsettled. It is no longer a seamless landmass, but a series of connected pieces tugging away from each other. This slow separation will eventually give rise to Laurasia in the north and Gondwana in the south. Two new supercontinents born from the divide. The continents are not merely drifting, they are alive with motion. They collide and crumple to form mountains. They slide past one another to cause earthquakes. They pull apart to birth new oceans. This is the story of plate tectonics, and it will continue shaping Earth for billions of years to come. As night falls on this ancient Earth, you watch the stars rise over the broken edge of Pangaea. The continents below you are still shifting, still whispering their long journey across time. And with every inch they move, a new chapter in the story of Earth is quietly being written. You continue your quiet journey above the ancient world, the air still warm and thick from the lingering humidity of Earth's deep past. Below you, Pangaea stretches wide, a colossal continent bound together like a giant puzzle. But now, it is beginning to show signs of strain. It is the late Triassic period, around 230 million years ago. The supercontinent that once stood united is quietly, invisibly starting to fracture. Not with dramatic explosions or crumbling cliffs, but with a slow, insistent pressure from within the Earth. Beneath the crust, in the mantle where molten rock churns in looping currents, the energy of the planet's interior continues to rise. These currents push and pull at the base of the tectonic plates, stressing the seams that hold Pangaea together. As you drift closer, you begin to see long, subtle rifts appearing, cracks in the crust where the land is being gently tugged in opposite directions. These aren't sudden tears, but slow partings, like clay stretched ever so gently until it thins and begins to split. These rifts begin to fill with magma from the mantle, which cools and hardens, creating new crust. This is how new oceans are born. One of the first great ruptures begins between what will one day be North America and Africa. The split is delicate at first, a mere thinning of land, but over millions of years it widens. Magma wells up in the gap, solidifying into fresh basalt rock. This is the birth of a mid-ocean ridge, and the early stirrings of what will one day become the Atlantic Ocean. You float over this growing scar in the Earth's surface. The land on either side of the rift is slowly drifting apart, just millimeters per year, yet steady and relentless. Imagine stretching a rubber band, not until it snaps, but until it silently pulls free. This is the quiet power of tectonic motion. As Pangaea begins to crack apart, its breakup is not symmetrical. The northern part of the supercontinent, Laurasia, will eventually split into North America, Europe, and Asia. The southern portion, Gondwana, will divide into South America, Africa, India, Antarctica, and Australia. Each of these landmasses begins its own long, slow journey, sailing across the surface of the Earth on the backs of the tectonic plates. As they separate, they pull the ocean floor open between them, forming great new basins that will one day be filled with seawater. Far below, the mid-Atlantic ridge begins to form, a vast undersea mountain range created by the spreading seafloor. Lava continues to erupt from deep fissures, creating new crust at the center, pushing the older crust outward. You might expect chaos, but the motion is graceful, deliberate, and constant. As continents drift apart, they carry with them the life forms that once shared a connected world. This separation will shape the evolution of species in powerful ways. Dinosaurs, in what is now South America, will follow different paths than those in what becomes Asia. Plants and animals, isolated by growing oceans, will evolve uniquely, adapting to their slowly changing environments. Meanwhile, Earth's surface changes in other ways. Mountain chains begin to appear where plates buckle and crumple. Shallow seas spread across lowlands. New coastlines form, eroded by wind and water. The geography of Earth becomes more diverse, more fragmented, and more beautiful. The cracking of Pangaea affects not just land, but the atmosphere and climate as well. As continents pull apart, air and ocean currents shift. Rainfall patterns change. Some areas grow lush and green, while others become arid. The long unity of Pangaea gave Earth a relatively uniform climate, but as the continents drift apart, regional climates begin to emerge. The early signs of deserts, monsoons, and ice caps. You soar over a forming rift valley, a long sunken scar in the land bordered by steep cliffs. The ground here has been stretched and dropped, creating a deep trench where a new ocean may someday grow. Water has already begun to seep into it, forming shallow lakes and narrow seas. The sun reflects off the still water, golden and warm, as if the earth is quietly healing from a slow tear. Now you move across the edges of the separating continents where volcanoes spring to life. These are not destructive catastrophes, but steady builders of new land. As magma rises through the thinning crust, it hardens into islands, ridges, and plateaus. You watch one such volcano, glowing gently in the twilight, its lava spilling down the slope into a fresh basin, creating land that has never existed before. In other areas, magma doesn't reach the surface, but pools just beneath the crust. This heat softens the surrounding rock, causing the land above to swell and crack. Over millions of years, these domes will become the seeds of future continental breaks. Still, the movement is not uniform. Some plates grind past each other rather than pull apart. In these regions, transform faults develop, zones where the crust is under lateral stress. One day, these will form places like the San Andreas Fault in California, where the Pacific Plate and North American Plate slide side by side. From above, you can now see Pangaea in transition. It is no longer one great land, but a mosaic of drifting masses. The once solid heart of the supercontinent is now laced with rifts, ridges, and new seas. Slowly, the familiar shapes of modern continents begin to emerge, like ancient spirits surfacing from the depths of time. You pass over what will become Greenland, still fused to Europe. Soon it will drift northwest, leaving behind the North Atlantic Ocean. To the south, India begins its long, lonely voyage northward across the Tethys Sea, racing toward Asia, a collision that will one day shake the world. Even now, new rifts are forming. The planet never stops shifting. The crust is like a jigsaw puzzle in motion, always changing, yet always fitting together. As you rise higher, you look down once more on Earth's surface, once unified, now scattered. The continents, like massive rafts, float ever so slowly atop the mantle's currents. You realize this movement has no end. The continents will continue to drift, collide, and reform for as long as the planet remains alive. In this quiet moment, you see Earth not as static, but as a living, breathing world, ever evolving, ever moving, guided by the deep and ancient rhythm beneath our feet. As you continue drifting high above the changing Earth, the scene below grows more dramatic. The smooth, slow separations you witnessed earlier have given way to something more forceful, more sculpted. Where continents once moved apart, now some begin to collide. Millions of years have passed since the cracking of Pangaea. The land masses have spread out, drifting on their tectonic rafts. But this movement does not go on in only one direction. Some plates are destined to meet again, and when they do not glide quietly past each other. Instead, they crash. But not like cars or crashing waves. The collisions here are slow, patient, and mighty. When two continental plates meet, neither sinks easily. Instead, the crust crumples and folds. Layer upon layer of rock is pushed upward, squeezed like clay by the enormous pressure of converging plates. These are the birthplaces of mountains. You float now above the edge of what will become the Appalachian Mountains. It is more than 300 million years ago, during the late stages of Pangaea's formation. Here, an earlier collision has already taken place, long before the Atlantic Ocean formed. A chain of islands and microcontinents slammed into the eastern edge of what is now North America, crumpling the crust and stacking rock upon rock, like folded blankets. You watch as jagged peaks rise slowly toward the sky, ancient ancestors to today's softened Appalachian hills. These mountains were once as tall as the Himalayas. Over time, they've worn down, smoothed by wind, rain, and the long passage of ages. But back in their prime, they towered over the land, evidence of Earth's incredible power to build, shape, and sculpt. You travel forward in time, across millions of years. Now, another continent, India, has broken free from Gondwana and is speeding northward across the Tethys Sea. At first, it sails alone, like a solitary leaf on a vast ocean. But it is on a collision course with Asia. The moment of impact doesn't happen all at once. It takes millions of years for India to fully meet Asia. When it does, something extraordinary occurs. The Indian plate doesn't dive beneath the Asian plate. Both are too buoyant, too thick. So instead, the crust folds. It rises. It shatters. And before your eyes, a mountain chain begins to lift from the earth. This is the birth of the Himalayas. You hover near the edge of this collision zone. The ground is heaving gently, an imperceptible rise that over millions of years becomes the tallest mountain range on Earth. Mount Everest, K2, Kanchenjunga, all born from this ancient, relentless pressure. Even today, the Himalayas are still rising, growing ever so slightly each year as the Indian plate continues to push against Asia. It is not just the land that transforms during these collisions. The rocks themselves change. Under intense pressure and heat, they fold, twist, and sometimes melt. Metamorphic rocks, once ordinary sediment or volcanic stone, become gleaming schist, shimmering gneiss, and brilliant marbles. The mountains become archives of ancient conditions, telling the story of their own birth through the very materials they're made of. From your vantage point, you watch a different kind of collision unfold, one where an oceanic plate meets a continental plate. Unlike the thick continental crust, oceanic plates are denser and thinner. When they collide with a continent, they often subduct, dive beneath the continental edge, and sink into the mantle. As the plate descends, it melts, feeding magma chambers that rise toward the surface. This is how volcanic mountain ranges form, not from the collision of land masses, but from the friction and melting beneath them. Along the edge of ancient South America, such a zone emerges, the beginnings of the Andes. One after another, volcanoes erupt. Lava pours from deep inside the earth, hardening into layers of igneous rock. Over time, these volcanoes grow taller and more numerous, forming a spine of peaks that stretches for thousands of miles. As you glide over these towering summits, you feel the contrast. The Himalayas, born from collision and crumpling, are largely made of pushed-up crust, their peaks crafted from once buried rock. The Andes, by comparison, are fiery, created by magma, volcanic ash, and repeated eruptions. Elsewhere in the world, the same story repeats in different ways. In Europe, Africa's slow northward drift eventually presses into the southern edge of the Eurasian plate. The result? The Alps. Their sharp ridges and lofty peaks echo the collision that continues even now. Every fold, every layer, every jagged cliff is a memory of land pressed against land. The process is ongoing. Even today, Earth's crust continues to buckle and rise. In places like the Himalayas, the Alps, and the Zagros Mountains in Iran, tectonic pressure builds inch by inch. Earthquakes rumble deep beneath the surface. gentle reminders that the plates are still restless. You glide now over a range that's just beginning to form, where the Red Sea is widening, slowly pushing Arabia away from Africa. In time, the edges of this separation will meet other plates and new mountains may grow. Each shift, each crack, carries with it the potential for upheaval and beauty. Even island chains like the Japanese archipelago or the islands of Indonesia owe their existence to subduction and collision. You pass over these islands, dotted with volcanoes and wrapped in green. Each one is a mountain rising from the sea, born of deep tension far beneath the waves. Back on the continents, erosion plays its part. The tallest mountains wear down slowly. Rain cuts channels into their slopes. Glaciers carve U-shaped valleys. Rivers carry dust and stone away, depositing them into seas and basins. And yet, as erosion lowers the peaks, tectonics often lifts them again. The balance is delicate, like an unending tug-of-war between sky and stone. From your quiet perch above the earth, you see the full picture, the mountain-building cycle in motion. Continental plates drift, collide, and compress. The crust thickens, mountains rise, and even as they erode, they leave behind highlands, plateaus, and ancient ranges softened by time. The Earth's mountains are not random or isolated.
They form long belts, often lining the edges of continents where collisions occur.
These belts are the scars of ancient impacts, records of where the Earth folded in on itself. And through it all, you notice something comforting. The pace of change is gentle, not sudden or violent, but persistent. It is the rhythm of the planet's breath, steady and certain. As the sun sets behind a towering peak, casting long shadows across a newborn range, you drift higher. The jagged edges of the world soften beneath the clouds. These mountains, once buried in the sea or buried under time, now stand tall, monuments to Earth's quiet, powerful dance. High above the Earth, you drift in silence, watching as the planet slowly reshapes itself. Below you, continents drift like islands on a great sea of rock. Mountains rise, oceans open, and coastlines evolve. But what orchestrates this movement? What invisible hand guides these massive slabs of land and sea? You peer beneath the surface, deep into the Earth's layers, and begin to understand the grand performance taking place. The crust you see is only the outermost shell. Below it lies the mantle, a vast layer of hot, slowly moving rock that churns with heat from the planet's core. And it is here, in this hidden realm, that the dance of the plates begins. The Earth's outer shell is broken into tectonic plates, immense, irregularly shaped sections of the crust and upper mantle. Some are vast, like the Pacific Plate, which stretches under a wide ocean. Others are smaller, like the Philippine Sea Plate or the Nazca Plate off the coast of South America. Each plate floats atop the asthenosphere, a softer, semi-fluid part of the upper mantle. Though solid, it moves ever so slowly, a river of rock flowing on geological timescales. These plates do not sit still. They are always in motion, carried by convection currents rising and falling in the mantle. Where hot material rises, plates are pushed apart. Where cool material sinks, plates are pulled downward. The entire system is dynamic, constantly rearranging the face of the Earth. You begin to observe their movements more closely. In one region, two plates are moving apart. This is a divergent boundary. You watch as molten rock from the mantle wells up, hardens, and forms new crust. This process creates mid-ocean ridges, vast underwater mountain chains that stretch for thousands of miles. The Mid-Atlantic Ridge, for example, runs like a seam between the Americas and Europe and Africa. Here, new ocean floor is born as the plates slowly pull away from each other. You follow the ridge northward, past Iceland, an island literally torn in two by tectonic motion. On this volcanic island, the Eurasian and North American plates are separating, pulling the island apart by a few centimeters each year. Fissures run through the landscape. Lava bubbles up in rift valleys. It is a place where you can stand with one foot on each plate, a visible reminder of the planet's motion. Next, you drift toward a place where two plates are sliding past one another. This is a transform boundary. At the San Andreas Fault in California, the Pacific Plate and North American Plate grind side by side. The motion is horizontal, not vertical, but this movement builds tension. When it is suddenly released, the ground shakes, an earthquake. These boundaries can remain quiet for decades, even centuries, only to unleash violent tremors in a single moment. You hover above this fault, feeling the tension in the air. The crust is stressed, bent, and strained. Though it appears calm, it holds potential energy that could one day reshape entire landscapes in seconds. And yet this too is part of the planet's rhythm, the shifting and sliding of a living world. Now you turn toward the most dramatic of all interactions, convergent boundaries where plates collide. These collisions are not always between continents. Often an oceanic plate collides with a continental plate, and because it is denser, the oceanic plate is forced beneath the continent. This is subduction. You follow one such boundary off the coast of South America. The Nazca Plate dives beneath the South American Plate, forming a deep trench along the ocean floor. The Peru-Chile Trench. Above this trench, the crust buckles upward, forming the Andes Mountains. Deep within the Earth, the subducted plate melts, feeding magma chambers that fuel volcanic peaks. This is how land is born, lifted from the sea by fire and pressure. You see similar zones across the world. The Mariana Trench, where the Pacific Plate descends beneath the Philippine Plate, the deepest point in the ocean. The Cascadia Subduction Zone in the Pacific Northwest, where volcanoes like Mount St. Helens lie quiet and watchful. And the Japanese Archipelago, a curved line of islands formed where the Pacific Plate subducts beneath the Eurasian Plate. Each plate boundary tells a story. Where plates meet, the Earth becomes restless. Earthquakes rattle the crust, volcanoes erupt in sudden fury. Yet it is from this very unrest that mountains rise and new crust forms. But the dance does not end with collisions. Some plates are squeezed from all sides and break into smaller plates. Others are trapped between larger neighbors and twisted into complex shapes. Over millions of years, these interactions can completely rearrange continents. You glide now above East Africa, where the African Plate is slowly splitting apart. This is the East African Rift, a zone of divergence where the continent itself is stretching and thinning. Lakes fill the depressions, Lake Tanganyika, Lake Malawi, while volcanoes like Mount Kilimanjaro rise nearby. Eventually, this rift may become a new ocean, dividing the continent in two. Even plate motion speeds vary. The Pacific Plate moves several centimeters each year, faster than fingernails grow. Other plates drift more slowly, yet their motion accumulates over time, reshaping the planet in vast and lasting ways. To help scientists understand this movement, GPS satellites track plate positions with stunning precision. Over decades, scientists have mapped the drift of continents, confirming that the plates move exactly as predicted by tectonic theory. The dance is real and ongoing. But plate tectonics affects more than just geology. It shapes the planet's climate. As continents drift, they change the positions of oceans and mountains, which in turn alter air and water circulation. These shifts can warm or cool the planet, trigger ice ages, or usher in periods of lush growth. For example, when India collided with Asia, the Himalayas rose and disrupted atmospheric circulation. They helped create the monsoon system that brings seasonal rains to South Asia, vital to ecosystems and human life. When the Isthmus of Panama rose, connecting North and South America, it changed ocean currents and may have helped bring on a global cooling trend. You begin to see the interconnectedness of everything: rock, water, air, and life. The plates move, and the world responds. Rain falls in new places. Animals migrate along fresh coastlines. Evolution, takes new turns. And all the while, the dance continues. Plates slide, drift, and dive. They build and destroy. They grind and glide. Sometimes with a thunderous quake, sometimes with the silent rising of a ridge. From your quiet vantage point above the Earth, the planet seems alive, not just in its forests and rivers, but in its very bones. The crust breathes, the mantle flows. The plates perform a dance that has lasted billions of years and will continue long after we are gone. You drift higher, leaving behind shifting boundaries and glowing magma plumes. The Earth below you spins gently, its surface a patchwork of motion. There are no straight lines, no final shapes, just endless change, measured in eons. Ahead lies another chapter in the story, how oceans opened and closed as the continents continued to move. You float in stillness above the ancient Earth, wrapped in the silence of deep time. Beneath you, the continents glide steadily across the surface like drifting ice flows. But your attention shifts now to something far greater in scale. The vast, deep expanses between them. The oceans. Though the land may seem the star of Earth's great tectonic drama, the oceans play an equally profound role. They grow and shrink, vanish and reappear, as if breathing in rhythm with the planet itself. Over hundreds of millions of years, the oceans have not simply been water-filled gaps between continents. They have been cradles of life, drivers of climate, and record-keepers of Earth's hidden history. Tonight, you explore their quiet transformation, how oceans came and went. Far in the past, long before humans, even before dinosaurs, there was an ocean called Pangaea, the mighty sea that once surrounded the supercontinent Pangaea. It was the most immense ocean Earth has ever known, stretching nearly pole to pole, its currents circulating freely around a single landmass. The waters were warm, rich with minerals, and teeming with early marine life. But as Pangaea began to crack and drift apart, Pangaea's once unbroken expanse began to change. The continents pulled away from one another, carving new channels and sea basins. These slowly filled with water from the surrounding ocean, forming entirely new bodies of water. You watch from above as a small rift between what will become Africa and South America begins to widen. At first, it is just a narrow valley. Then, over millions of years, the rift deepens and lengthens. Water begins to rush in from Pangaea, filling the depression. The basin grows wider still, and eventually, a new ocean is born. The Atlantic. You hover over its early formation, watching as volcanic ridges rise in the middle of the spreading seafloor. The Mid-Atlantic Ridge. This underwater mountain chain forms as molten rock from the mantle rises to fill the gap between separating plates. It's a quiet, persistent process. Crust is created, inch by inch, forming the very floor of the Atlantic Ocean. This seafloor, you realize, is young, constantly renewed at the ridge, and slowly pushed outward over time. Unlike the stable rocks of the continents, oceanic crust is recyclable. Where it forms in the center, it must eventually disappear at the edges. And so for every ocean that opens, another must begin to close. You drift toward a different part of the globe, the Pacific Ocean. It's vast now, but shrinking. Along its edges, especially the so-called Ring of Fire, the seafloor is slowly being consumed as oceanic plates dive beneath continental ones. The Pacific plate is being pulled into deep subduction zones, where it melts into the mantle. This process is called the Wilson cycle, the opening and closing of oceans over immense stretches of time. It begins with rifting and divergence, grows into a full ocean basin, and ends with convergence and subduction as continents move back toward one another. You now visit a place that tells a quieter story of a long-lost sea. Between the slowly separating landmasses of Laurasia and Gondwana, an ancient ocean once stretched wide, the Tethys Sea. It flowed where the Mediterranean, Black, and Caspian seas exist today. In its prime, the Tethys was warm, shallow, and full of coral reefs and marine creatures. But as Africa, India, and Arabia drifted northward, the Tethys began to narrow. Bit by bit, it was squeezed shut by the approaching continents. You hover above its remnants, the shrinking Mediterranean and Caspian basins, surrounded now by towering mountains like the Alps, Zagros, and Himalayas, all born from the closing of that ancient sea. Sometimes oceans disappear entirely, leaving behind traces. If you look closely, you can still find the whisper of long-vanished seas etched into the rock. Marine fossils high in the mountains, salt layers deep underground, and limestone formed from ancient coral beds. These are the records of oceans that no longer exist. And what of inland seas? Not all water lies between continents. At various times in Earth's history, shallow seas have covered vast portions of land. During the Cretaceous period, much of what is now North America was submerged beneath the Western Interior Seaway, a warm, shallow body of water that split the continent in two. You fly over this ancient sea, watching long-necked marine reptiles glide beneath the surface, while winged pterosaurs soar above. The seaway is gone today, replaced by prairies and plains, but deep in the soil lie the remains of its vanished tides. In another era, Europe was little more than a chain of islands, scattered across a shallow sea. The Paris Basin, the North Sea, and parts of the Alpine foothills still carry the fossils of marine creatures that once lived in those submerged lowlands. The oceans shape the land in other ways, too. As continents drift, they can change the depth and shape of ocean basins, which in turn affect sea level. During times of intense tectonic activity, when seafloor ridges are spreading rapidly, the oceans are shallower and water spills onto the continents. In quieter times, deeper basins pull water away and coastlines retreat. You follow the retreat of an ancient shoreline, watching forests become deserts and marshes turn to plains. Over millions of years, these shifts determine where rivers flow, where climates develop, and where life can thrive. Even climate patterns are shaped by the movement of oceans. As new oceans form or old ones close, they redirect ocean currents, which carry warm and cold water around the globe. When South America connected to North America, it blocked the flow between the Pacific and Atlantic, changing currents and helping ice sheets grow in the northern hemisphere. And when Antarctica finally broke away from Australia and South America, a circumpolar current began to circle the southern pole, isolating the continent and plunging it into permanent ice. The oceans, then, are not static features of Earth. They are sculpted by plate tectonics and in turn sculpt the world around them. Their boundaries are flexible, their presence fleeting. They can span the globe or vanish into folded mountains. You now fly low over the ocean floor itself, a hidden world few have seen. There are deep trenches, such as the Mariana Trench, nearly 11 kilometers below the surface. There are abyssal plains, vast and dark. There are hydrothermal vents where life thrives in total darkness, fed not by sunlight, but by chemicals from deep within the earth. The oceans hold more than water. They hold secrets, from ancient seaways to continents yet to rise. As you rise again into the night sky, you glimpse the curved edges of the continents below. Between them stretch oceans, both old and new, filled with stories written in salt and stone. And as the plates continue to shift, so too will the shape of the seas, ever changing, ever returning, a fluid memory of Earth's restless surface. Next, we journey deeper into the engine of all this motion, the mantle. You drift now toward the heart of Earth's power, not the mountains that rise or the oceans that swell, but the deep, slow forces that move everything above. Beneath the crust, under the shifting plates and drifting continents, lies a world that few have imagined, but that controls the fate of every rock, every sea, every continent. Tonight, we descend into the mantle, Earth's great engine, and meet the glowing rivers of magma that give birth to mountains, tear continents apart, and reshape oceans across the ages. The Earth, as you now understand, is not a solid stone from core to surface. It is layered, like an onion. Each shell different in temperature, pressure, and behavior. At the very center lies the inner core, a dense ball of iron and nickel, solid despite its incredible heat. Around that, the outer core, a swirling ocean of molten metal. It is this movement, that generates Earth's magnetic field. But above that, stretching for nearly 3,000 kilometers, lies the mantle, a world of rock, so hot that it moves not like stone, but like thick, slow honey. It is not liquid, not quite solid, but something in between, a creeping, convecting sea of heat and motion. You drift into this deep layer now, down past the crust, past the plates. The temperature rises, the light fades. Around you, pressure builds. The rock is glowing in deep reds and orange golds, slowly shifting, almost breathing. This is the asthenosphere, the upper portion of the mantle, and the layer upon which tectonic plates float. It is here that convection currents rise and fall. Hot material from deeper in the mantle slowly moves upward. As it nears the cooler upper mantle and crust, it spreads outward, losing heat. Then, heavier and denser, it sinks back down. Over millions of years, these currents form slow, swirling loops, Earth's version of weather, but on a much longer scale. You begin to see how these currents drive the motion of the plates above. Where hot mantle pushes up, plates are forced apart. Divergent boundaries. Where cold mantle sinks downward, it drags plates into the Earth. Subduction zones. This entire cycle is what powers plate tectonics. Without the mantle's heat and movement, the continents would sit still, and Earth would be silent. Occasionally you notice something unusual, a narrow column of especially hot mantle rock rising directly from deep within the planet, a mantle plume. These plumes can punch through the crust, creating chains of volcanoes. You follow one now, the plume that formed the Hawaiian Islands. As the Pacific plate slowly moved over this stationary plume, magma burst through the crust in one place, forming an island. Then, as the plate shifted, the hot spot remained, creating a new island nearby, and then another. One by one, a string of islands formed, each a monument to the power rising from the deep. Not all mantle plumes form ocean islands. Some create vast volcanic regions on land. You glide toward Iceland, perched atop both the mid-Atlantic ridge and a powerful mantle plume. Here you see magma erupting from great fissures, building new land, warming rivers, and fueling geysers. The mantle's fire reaches the surface in spectacular ways. Deeper still, you find areas where heat pools silently beneath thick crust. In places like Yellowstone, the surface may appear calm, even peaceful, but far below a vast chamber of magma simmers, stretching for miles. This, too, is the work of the mantle, slow, hidden, and immensely powerful. The composition of magma changes depending on where it forms. Magma that comes from ocean ridges is rich in iron and magnesium, basaltic magma, and flows easily, forming broad, low volcanoes like those in Hawaii. Magma formed in subduction zones contains more silica, andesitic or rhyolitic magma, and is thicker, more explosive. These magmas form towering stratovolcanoes, like Mount Fuji or Mount St. Helens. You begin to see how magma shapes the Earth not just through eruption, but through the slow process of intrusion. Sometimes, magma doesn't reach the surface. Instead, it hardens underground in veins, domes, or massive chambers. Over time, erosion wears away the rock above, revealing these plutons, the silent architecture of Earth's interior. In places where the crust is pulled apart, such as in rift zones or mid-ocean ridges, magma rises to fill the gaps. You fly over one such place now, the East African Rift. Here, the continent is stretching, and magma seeps up through fractures in the crust. Volcanoes like Mount Nyiragongo and Erta Ale erupt regularly, building land and splitting the Earth. Elsewhere, in the Basin and Range province of North America, you witness how stretching crust creates fault block mountains, while underlying magma alters the landscape from below. These regions may not have dramatic volcanoes, but they tell the same story. The crust is being changed from beneath. All of this, every ridge, every volcano, every drifting continent, is fueled by the mantle's heat. But where does this heat come from? Much of it is primordial, left over from Earth's violent formation over 4.5 billion years ago. When dust and rock collided to build the planet, the energy of those impacts was trapped inside. Some of the heat comes from the radioactive decay of elements like uranium and thorium in the mantle. As these atoms break down, they release energy, warming the surrounding rock. This heat doesn't escape quickly. Rock is a poor conductor, and Earth's size ensures that heat is held for billions of years. Slowly, steadily, it rises through the mantle, creating convection, driving plate motion, and feeding the planet's geological life. You drift deeper still, toward the lower mantle. Here, pressure is immense, enough to change the structure of minerals themselves. You see olivine, the green mineral common in the upper mantle, slowly transform into denser forms like wadsleyite and ringwoodite. These changes absorb and release heat, influencing how the mantle flows. The deeper you go, the slower everything becomes. But even here, in the transition zone between the upper and lower mantle, movement continues. You sense a pulse, a slow heartbeat of the Earth, as heat makes its endless journey upward. You begin to ascend now, rising back toward the crust. As you pass upward through the mantle, you carry with you a deeper understanding. The Earth's surface is just the visible edge of something much larger. What seems solid and unmoving above is in fact a living shell, powered by unseen forces far below. Without the mantle's flow, there would be no drifting continents, no earthquakes, no volcanoes, no mountains or rift valleys. The land we know is merely the skin. The motion comes from within. As you break once more through the crust and return to the surface, you see the continents continuing their slow journey. The oceans ripple. Volcanoes glow in the distance. The story of Earth is still unfolding, written in magma, carried by the mantle's endless breath. Now, with this knowledge in hand, we return to the surface world to witness how drifting continents shaped the time of the dinosaurs. You rise again to the Earth's surface, warm air brushing gently past as you glide over a world in motion. The continents, no longer one great supercontinent, have separated into massive, drifting land masses. Oceans stretch wide between them. Mountain chains begin to rise, and all across the land, life flourishes. It is the Mesozoic era, a span of time lasting nearly 186 million years, and you are now drifting through the age of the dinosaurs. This age is divided into 3 long chapters: the Triassic, Jurassic, and Cretaceous periods. It begins around 252 million years ago, just after the greatest extinction Earth has ever known, and ends around 66 million years ago, with another, more familiar extinction that marks the end of the dinosaurs' reign. Through it all, the continents are on the move. You look down upon what was once Pangaea. By the early Jurassic, the great supercontinent has begun to fragment. The northern half, Laurasia, is slowly pulling away from the southern landmass, Gondwana. Between them, a narrow sea has opened, the infant Atlantic Ocean. Over time, this crack will widen into the broad ocean we know today. As Laurasia drifts northward, it breaks into North America, Europe, and Asia. Gondwana, too, begins to fracture, splintering into South America, Africa, India, Antarctica, and Australia. From above, you see a slow ballet unfold. These continents drift gradually, but their movement creates massive change. Climate zones shift, seas open, animals migrate, ecosystems transform. You drift lower now, soaring above the dense ferns and towering conifers of the Jurassic forests. Below, giant herbivorous dinosaurs like Diplodocus and Stegosaurus move in slow herds, while predatory Allosaurus stalks the shadows. The landscape is rich and humid, filled with insect song and the soft calls of early birds. The drifting continents shape everything. As South America and Africa separate, a broad rift valley forms, one day to become the South Atlantic Ocean. You see volcanic activity along the rift's length, as magma from the mantle wells up to form new seafloor. Lava cools into basalt, forming the oceanic crust. Slowly, the continents pull apart. This widening ocean influences the world's climate. With more open water, ocean currents change, redistributing heat across the planet. Rainfall patterns shift. Some places become wetter, others drier. In the heart of Gondwana, India begins its lonely journey northward. At first, it moves slowly, still connected to Madagascar. But soon it breaks away and sails alone across the Tethys Sea, heading toward a distant collision with Asia. A moment that won't occur for tens of millions of years, but will one day give rise to the Himalayas. You pass over North America, where the drifting plate has caused the western edge to press against the Farallon plate, an oceanic plate slowly subducting beneath it. This collision causes mountain building, the early stages of what will become the Rocky Mountains. Volcanoes dot the landscape, and inland seas begin to appear. The slow movements of Earth's crust also shape where life can live. During the Cretaceous period, global sea levels rise. Warm, shallow seas flood much of the low-lying continents. You glide over what is now the central United States, submerged beneath the western interior seaway, a vast inland ocean stretching from the Gulf of Mexico to the Arctic Ocean. Marine reptiles like Mosasaurus and Plesiosaurus swim beneath you, while flocks of flying pterosaurs glide above the waves. On the nearby shores, the Earth teems with life. Flowering plants appear for the first time, spreading quickly across the globe. Their arrival transforms entire ecosystems. You drift eastward toward what will one day be Europe. In the Cretaceous, it is a scattered chain of islands in a warm, shallow sea. The climate here is balmy. Thick jungles grow on the islands. Dinosaurs like iguanodon wander beneath the trees, and small feathered creatures flutter through the canopy. Early birds, descendants of the theropod dinosaurs. The drifting continents also create barriers, oceans and mountains that isolate populations. This leads to evolutionary branching. Species on one continent become different from their relatives on another. Dinosaurs in South America evolve into unique forms, separate from those in North America or Asia. You hover over Gondwana, now in pieces. On Australia, early marsupials begin to evolve. On Antarctica, which is not yet frozen, forests still grow, and dinosaurs roam through the southern twilight. The climate here is cooler but still temperate. The ice sheets have not yet come. As the Cretaceous period draws to a close, the continents are closer to their modern positions. North America and Europe are separated by a widening Atlantic. India continues its northward race. Africa moves steadily toward Europe. Australia begins to drift southeast. The pieces are falling into place, slowly and silently. And then, in the sky, something changes. You look up to see a faint shimmer, a distant object falling toward Earth. It is the end of the Mesozoic. An asteroid, nearly 10 kilometers wide, is hurtling toward the planet. It strikes what is now the Yucatan Peninsula in Mexico. With the force of billions of nuclear bombs, the world plunges into darkness. Fires rage, ash clouds block the sun, temperatures fall, plants wither. Dinosaurs, unable to cope with the sudden change, begin to vanish. But even in this moment of extinction, the continents continue to move. The mantle still flows, the plates still drift. And in the shadows of the catastrophe, mammals begin to rise. From above, you see the smoke clear. The skies lighten, forests slowly return, new animals emerge, and the continents, still in motion, continue shaping what comes next. The age of dinosaurs has ended, but Earth's journey has only just begun. The Earth turns gently beneath you, and the continents continue their silent voyage across the surface of the world. The age of dinosaurs has ended, and the planet is beginning a new chapter. As life recovers and mammals begin to flourish, one continent in particular is racing northward, small compared to some, but on a course that will change the face of the world forever. That continent is India. You hover above it now, around 65 million years ago. The landscape is vast and volcanic. The skies are filled with haze from eruptions, and the land is scarred by vast lava flows known as the Deccan Traps. These eruptions have poured rivers of basalt across the land, and some scientists believe their gases may have even contributed to the extinction that ended the dinosaurs. But this is only the beginning of India's journey. India is moving unusually fast. By tectonic standards, it's a speeding bullet. While most continents drift along at a few centimeters per year, India is moving north at nearly 15 to 20 centimeters per year. Driven by strong mantle currents, it races across the Tethys Sea, leaving its southern companion, Madagascar, behind. The Tethys is narrowing. A warm, shallow sea once filled with coral reefs, ammonites, and ancient fish. As India cuts through it, the ocean's space shrinks. Ahead lies Asia, still vast and spreading, and the two land masses are destined to collide. You fast forward through time. The Tethys disappears inch by inch. Coral reefs crumble, sediment piles along the leading edge of both continents, and then, around 50 million years ago, the first contact occurs. But this is not a crash in the way you might imagine. It's not sudden or explosive. It's a long, slow, unyielding collision. Two massive bodies of crust press into each other, and because both are continental plates, neither will subduct easily. Instead, the crust between them folds and buckles, layer upon layer, like cloth pushed together on a table. You watch, spellbound, as the surface begins to rise. This is the birth of the Himalayas, the highest mountain range on Earth. What began as sediment at the bottom of an ocean is now being lifted into the sky. Rock that once lay beneath coral beds and shallow lagoons becomes Mount Everest, Lhotse, and Annapurna. The process is slow but relentless. For millions of years, the Indian plate continues to push northward, crumpling the crust and thickening it. The mountains rise higher and higher. Even today, the collision is not over. India is still moving, and the Himalayas still rise at a rate of about 5 millimeters per year. You float above the Tibetan Plateau, just north of the mountains. It's the largest and highest plateau on Earth, a vast uplifted region that once lay at sea level. Now it towers 3 miles into the sky. Glaciers etch patterns into its surface. Rivers born from its snow feed the great waterways of Asia, the Ganges, Yangtze, Mekong, and Brahmaputra. This collision does more than shape mountains. It changes the climate. As the Himalayas rise, they become a massive wall that blocks moist air from the Indian Ocean. Warm, wet winds slam into the mountains and are forced upward, cooling and condensing into rain. Thus begins the monsoon system, a seasonal pattern of rains that sustains crops, rivers, and ecosystems across South Asia. On the northern side of the mountains, the air is dry and rainless. The Tibetan Plateau becomes arid, and beyond it lies the Gobi Desert. The collision has literally reshaped the weather. Below you, animals evolve to match this new terrain. High-altitude creatures adapt to thinner air and colder climates. Snow leopards, yak, and hardy shrubs begin to define the ecosystem. What was once seafloor is now sky, and life finds a way to thrive. Geologists, millions of years later, will find the fossils of marine creatures high in the Himalayas. Ammonites, corals, and shells from long dead seas, trapped in limestone, folded into the peaks. These remnants tell the story of India's journey, hidden in stone. You follow the Indus River down from the mountains. It cuts through valleys carved by glacial melt, winding through deep gorges. The land below is fertile and green. Civilizations will one day flourish here, drawn to the rivers born from the clash of continents. But the Himalayas are not the only result of India's collision. To the southeast, the pressure of the impact has caused cracks and shifts all across Southeast Asia. Mountain ranges ripple through Myanmar, Thailand, Vietnam, and China. These are the distant echoes of the same tectonic force. Even earthquakes bear witness to the ongoing movement. You watch from above as pressure builds silently in the crust. Faults shift. Stress accumulates. Then, with a deep, distant rumble, the ground jolts. These are the Himalayan earthquakes, reminders that Earth's plates are still restless, still colliding, still sculpting. India's collision with Asia is one of the most dramatic tectonic events in the planet's recent history. It's a rare example of a continent-continent collision, and it continues to this day. As you float above the jagged white peaks of the Himalayas, their snow gleaming in the sun, you feel the deep time beneath you. These mountains, so timeless and unmoving to the human eye, are in fact young by geological standards. They are a moment in Earth's living story, still growing, still changing. The rocks here whisper of oceans long gone. The air carries winds redirected by newly risen heights, and the rivers cut paths through valleys that did not exist a few million years ago. You rise higher now, looking out across Asia. To the west, the collision has bent and broken the crust all the way into the Iranian Plateau and Zagros Mountains. To the east, it has nudged the edge of China, forming ranges like the Qinling and Hongduan. India's journey, a continent crossing an ocean and reshaping another, is not unique. But it is one of Earth's most powerful reminders that continents are not fixed. They are voyagers. They float, collide, and carry the memory of the planet's inner fire wherever they go. And with every mountain they raise, they leave behind clues. Rocks twisted by pressure, fossils lifted to the sky, rivers rerouted, climates altered. The Himalayas stand now as a monument, not just to the might of collision, but to the quiet, ceaseless motion beneath our feet. From here, your journey continues to an even colder and more dramatic chapter: the rise of the ice ages and the chill of drifting continents under a changing sky. The earth beneath you turns cooler now. The once steamy, jungle-covered world of the dinosaurs is gone. As you drift quietly across the changing surface, the air begins to sharpen, the skies take on a pale silver hue, and the lands below start to shimmer with frost. The age of warmth is passing. You are entering the world of ice ages. Vast, repeating eras when snow and ice stretched far from the poles and Earth shivered under their heavy breath. But this chill did not arrive suddenly. It crept in, shaped and stirred by the slow dance of drifting continents and the deep rhythms of Earth itself. You begin this part of the journey around 34 million years ago. The continents have drifted into new positions, and these new arrangements begin to alter the planet's climate. To the south, you see Antarctica, once connected to other land masses, now floating alone at the bottom of the world. It was once green, forested, even warm in places, but now, isolated by the circumpolar current, cold water circles the continent without interruption. This powerful ring of water acts like a thermal barrier, trapping the cold in and keeping the warmth out. The result is dramatic. Temperatures drop, snow begins to fall and stay. Year after year, the layers pile up, glaciers form, and slowly, over time, ice sheets begin to grow. Antarctica transforms into the frozen continent we know today, a white, shimmering expanse that reflects sunlight back into space and helps cool the entire planet. You hover above the growing ice, watching as it spreads inland, carving valleys, pressing down the crust with its weight. The temperature of the Earth falls in response. But Antarctica is not alone in this transformation. To the north, you turn your gaze to Greenland. Once a warm forested island, it too begins to cool. Around 2.6 million years ago, ice begins to appear in the northern hemisphere. Snow no longer melts in summer. Glaciers stretch across Canada, Scandinavia, and Russia. The planet enters the Quaternary period, marked by the rise and fall of glacial cycles. Long sweeping ice ages, each lasting tens of thousands of years. You glide over North America as the most recent glacial period unfolds. Massive sheets of ice, the Laurentide ice sheet among others, spread southward. Cities that exist today, like Chicago, Toronto, and New York, are buried beneath a mile of ice. Trees vanish. Lakes freeze. The land groans under the pressure. But how did the drifting of continents help cause these frozen ages? You rise higher to view the world's layout. It is the position of the continents, now clustered closer to the poles, that allows for large sheets of ice to build up. When land is situated near the poles, snow has a place to accumulate and grow. In earlier ages, when continents were closer to the equator, the Earth was far warmer and the planet had no major ice caps at all. In addition to continental position, other factors join the chorus. The opening and closing of ocean gateways, like the Drake Passage between South America and Antarctica or the Isthmus of Panama, alter ocean circulation. These changes redirect warm and cold currents, affecting where heat travels across the planet. For instance, once South America and North America connect fully, warm currents from the Pacific are blocked from flowing into the Atlantic. The Gulf Stream strengthens, sending warm water to northern Europe, but also increasing evaporation, which leads to more snowfall in the Arctic. This creates the perfect conditions for long-term ice buildup. As continents continue their slow journey, the planet's climate pulses in long, steady cycles. You glide above Europe, now shivering beneath sheets of snow and ice. Glaciers carve great U-shaped valleys into the land, grind mountains down into ridges, and create thousands of freshwater lakes. Rivers shift courses. The weight of the ice compresses the land, pushing it down, land that will slowly rebound once the glaciers melt. The pattern becomes clear. Glacial periods arrive, and then, when conditions change, they retreat. The ice melts, rivers swell, seas rise, and then, thousands of years later, the cold returns again. These are the Milankovitch cycles, natural changes in Earth's orbit and tilt that, combined with continental positions and greenhouse gases, trigger the advance and retreat of the ice. Each cycle stretches over tens of thousands of years, bringing alternating eras of cold and warmth. You drift over the Sahara Desert, today one of the hottest, driest places on Earth. But during the last glacial maximum, parts of it were green, dotted with lakes and grasslands. Climate is not fixed. It shifts with the land and sky. As you soar above Asia, you see the lush plains of China, dusty, wind-blown soils that were once created by glacial grinding and carried by cold winds. You follow these winds west, across the Caspian Sea, over the Alps, and across the European plains, where early humans once walked among mammoths and woolly rhinoceroses. You pass over vast permafrost zones, where the ground remains frozen year-round. Beneath the surface lies not only ice, but also carbon, trapped for tens of thousands of years. As the climate warms and ice retreats, some of this carbon will be released, feeding back into the cycle and influencing the next chapter of Earth's story. But the ice does not only affect land. You turn toward the seas. During glacial periods, so much water is locked in ice that sea levels fall, sometimes by over 100 meters. Entire land bridges emerge. Siberia connects to Alaska through the Bering Land Bridge, allowing animals, and eventually humans, to cross into new continents. Britain connects to Europe. Australia links with New Guinea. The world becomes briefly more accessible. Then, as the ice melts, the oceans rise again. Coastlines retreat. Islands form. Some lands are lost beneath the waves. Forever. You witness the transition into the Holocene, the warm period we live in today. Around 12,000 years ago, the last ice age ended, glaciers retreated, forests returned, lakes and rivers reappeared. Human civilizations began to flourish. But even now, in this time of relative warmth, the memory of the ice remains. You can still see the scars it left behind. The glacial lakes of Canada, the fjords of Norway, the drumlins and moraines scattered across northern Europe. These are Earth's fingerprints from the cold. And the continents, though slow and quiet, are still drifting, still shaping climate, still guiding the dance of snow and warmth. Antarctica remains locked in ice. Greenland still holds its frozen crown. And in the far north, the Arctic ice ebbs and flows with the seasons. As you look down one final time on this chilled Earth, you realize something profound. The ice ages are not ancient history. They are part of a living cycle, one that continues, shaped by the land, the sea, the sun, and time. Now let us dive beneath the oceans once again to find lands not above the surface, but hidden beneath the sea. As you drift once again over the blue expanse of Earth's oceans, the world below you seems serene and familiar, vast stretches of open water broken only by the occasional island or ripple of waves. But beneath the surface lies a hidden story, one that few have ever seen. The story of continents beneath the sea. For while we often picture continents as the great landmasses that rise above sea level, the truth is more mysterious. Some pieces of Earth's continental crust lie sunken and submerged, lost beneath the ocean surface, forgotten fragments of long-vanished worlds. You descend slowly through the water, the light dimming with each passing meter. Soon you reach the continental shelf, a gentle slope that extends from the shoreline before plunging into the deep ocean. This shelf, though underwater, is still part of the continent. It's a submerged extension of land, home to coral reefs, kelp forests, and thriving marine life. But deeper still lie secrets even older. You glide southward now toward New Zealand, and then east into the Pacific. Here, the seafloor rises subtly beneath the water, not enough to break the surface, but enough to form a vast plateau. This is Zealandia, a nearly submerged continent. Once connected to Gondwana, Zealandia broke away around 80 million years ago and began to drift. But instead of rising into towering landmasses like other continents, it stretched and thinned as it moved, eventually sinking beneath the sea. Today, only a tiny portion of Zealandia remains above water, the islands of New Zealand and New Caledonia. But if you could drain the ocean here, you would see an enormous sunken land, nearly half the size of Australia, complete with ridges, basins, and mountain chains. Scientists only recently recognized it as a continent in its own right, a reminder that not all continents need to rise above the waves. You drift west, over Sundaland, another submerged landmass. During the ice ages, when sea levels were lower, much of Southeast Asia was connected. The islands of Borneo, Sumatra, and Java were part of a continuous land bridge that extended into mainland Asia. You glide over the shallow South China Sea, seeing the shape of this drowned world beneath the waves. As the ice melted and oceans rose, these lands were slowly consumed by water. What was once forest and plain is now seafloor. Elsewhere in the Indian Ocean, you encounter Mauritius, a sliver of ancient continental crust buried beneath volcanic islands. It lies beneath Mauritius, an island formed by volcanic eruptions, but hidden below its lava lies something older, a fragment of land that broke off from India as it drifted away from Madagascar nearly 85 million years ago. These sunken continents are rare and fragile. Unlike oceanic crust, which is dense, young, and formed at mid-ocean ridges, continental crust is lighter, thicker, and much older. It floats higher on the mantle, which is why most of it stands above sea level. But under certain conditions, when stretched thin or torn apart, even continents can drown. You float toward the Kerguelen Plateau, another sunken continent in the southern Indian Ocean. This massive underwater feature, larger than Texas, was once above sea level, possibly supporting forests and rivers. Around 100 million years ago, it began to sink, pulled down by shifting tectonic plates and mantle plumes. Today, it lies beneath 2 kilometers of water. Not all submerged lands are as ancient. Some are the result of more recent volcanic or tectonic activity. You drift above the Azores Plateau, near the Mid-Atlantic Ridge, a volcanic rise where magma from deep within the Earth pushes upward, creating new seafloor and occasionally lifting blocks of crust. You see islands like Iceland perched atop such ridges. Though they appear isolated, they are often the visible peaks of vast underwater landforms. ridges that stretch for thousands of kilometers beneath the ocean. You glide next over the Ontong Java Plateau, north of Australia, one of the largest volcanic provinces in the world. Formed by a massive outpouring of magma around 120 million years ago, it covers an area larger than Alaska. Though not continental crust, it is a reminder of how the seafloor itself can be shaped by forces usually reserved for continents. But how do scientists find these hidden lands? You peer downward and see sonar waves bouncing off the seafloor. Bathymetric mapping, much like radar, allows ships to see the contours of the ocean floor. Seismic waves help reveal the structure of crust beneath layers of sediment. And rock samples, dredged from the deep, reveal ancient granite and quartz, clear signs of continental, not oceanic origin. Some submerged lands reveal themselves through their fossils. You drift over underwater plateaus where scientists have found microfossils, the remains of tiny land plants or animals that once lived in freshwater, buried beneath layers of marine sediment. You imagine draining the oceans entirely. What you'd see would astonish you. Mountain ranges stretching across basins, sunken valleys, ridges taller than the Rockies, and fragments of ancient continents hiding in the shadows. Even the Atlantic Ocean, still widening today, hides bits of lost land. Between Europe and North America lie buried microcontinents, fragments from the breakup of Pangaea. These sunken relics are remnants of the Earth's shifting puzzle, reshaped by time and buried by the sea. And beyond the present, you imagine the future. What if sea levels rise again? If tectonic forces pull a continent down? Will today's familiar lands become tomorrow's underwater plateaus? Earth's surface is never fixed. The boundary between land and sea is a fleeting line, drawn and redrawn by plate movement and time. You rise now, high above the Earth, looking down at the blue oceans. You know that beneath the surface, hidden from the eye, are worlds we've only just begun to uncover. Lost continents, fractured shelves, and sunken histories. And still, the continents continue their journey. One of them, Africa, is showing signs of change, not at the edges, but deep within. A slow tear is forming. A new chapter is beginning. Let us turn now to this unfolding story, the slow rift in the heart of a continent. You now drift gently over the vast and ancient continent of Africa, a land carved by time, shaped by rivers and deserts, and rich in both human and geological history. Beneath the savannas and mountains, however, something remarkable is happening. Africa, a single great landmass for hundreds of millions of years, is slowly beginning to tear apart. This is not a sudden or violent split, but a rift, a slow, quiet stretching of the Earth's crust. It begins so subtly that even the animals grazing across the plains or the people living along the valleys might not sense it. But if you look deeper beneath the soil and stone, you can see the signs. Africa is being rifted, pulled in two directions, and the land between is sinking. You are hovering above the East African Rift System, a scar that stretches more than 6,000 kilometers from the Red Sea in the north all the way south through Ethiopia, Kenya, Tanzania, and into Mozambique. This rift is one of the most dramatic examples of continental breakup on Earth, a place where a continent is visibly and measurably coming apart. From above, the landscape appears cracked and broken in places. Long valleys stretch for hundreds of kilometers, flanked by steep escarpments. In between lie high plateaus, lakes, and volcanoes. These are the early signs of what, in tens of millions of years, may become a new ocean basin. You descend toward the rift, drifting along the Great Rift Valley. Beneath your feet, the Earth's crust is being pulled thin. As it stretches, faults form, giant cracks where blocks of crust sink downward. These graben, sunken blocks, are the floor of the Rift Valley. Flanking them are horsts, the uplifted blocks of land that form the high escarpments on either side. In some regions, like Afar in Ethiopia, the rift is widening at a rate of a few millimeters to centimeters per year, the same rate your fingernails grow. It seems small, but over time this motion will create something enormous. You follow the rift north, toward the Danakil Depression, one of the hottest and most geologically active places on Earth. The ground here is low, dry, and otherworldly, colored by minerals and bubbling with acidic pools and steaming vents. This is where three tectonic plates, the African, Somali, and Arabian plates, meet in a triple junction. You see cracks forming in the crust. Lava oozes from the earth, creating new land. The rift here is still young, but it is growing. To the south, the rift passes through Kenya and Tanzania, where it creates towering mountains and deep lakes. Mount Kilimanjaro and Mount Kenya, both volcanoes, rise near the rift's edge, monuments to the molten rock moving beneath. These volcanoes, born of tension and magma, stand watch over the land as the rift continues to evolve. You drift above Lake Tanganyika, one of the deepest freshwater lakes in the world. It fills a rift valley that plunges deep into the Earth's crust. To the west lies Lake Albert, and to the east, Lake Malawi, all formed by the stretching and sinking of the land. These lakes are long and narrow, bordered by steep cliffs, and filled with ancient, diverse life. The rifting doesn't just change the surface, it reshapes ecosystems. As the land splits, rivers change course, rainfall patterns shift, and new habitats emerge. In the rift valleys, isolated lakes become cradles of evolution. Unique species of fish, birds, and mammals arise in response to these isolated conditions. Even humans have been shaped by this land. You float over Olduvai Gorge in Tanzania, where some of the earliest fossils of our human ancestors were discovered. It is no coincidence that the Rift Valley is one of the richest sites for hominin fossils. As the rift formed, it created lakes and savannas, which attracted early animals and the humans who hunted them. The rift also preserved bones in layers of volcanic ash and sediment, giving us a detailed record of our deep past. You can almost hear the distant footsteps of early humans walking across the rift floor, stone tools in hand, their lives entwined with this restless earth. But what is causing this massive split? The tectonic plates beneath Africa are slowly separating. The main plate, known as the African plate, is breaking into two. The western portion will remain Africa, and the eastern part is known as the Somali plate. As the plates pull apart, the crust between them thins and stretches, creating faults and valleys. Beneath the rift, you find the same engine seen elsewhere. Mantle plumes. Hot rock rises from deep within the earth, softening the crust and pushing it upward. You see magma chambers beneath the rift zones, feeding volcanoes and geysers. The heat weakens the lithosphere, making it easier for the rift to grow. In the future, perhaps 10 to 20 million years from now, this rift may open fully. The eastern portion of Africa could break away, forming a new continent. The Rift Valley would become a newborn ocean, filled with seawater that floods in from the Red Sea. Volcanic islands would rise from its depths, and the highlands of Ethiopia and Kenya would become distant shores. From above, you can already imagine it, a new ocean basin forming where today there are deserts, rivers, and farmland. A great transformation unfolding too slowly for a single lifetime, yet inevitable in the grand scale of Earth's history. The rifting of Africa is one of many such stories on our planet. Pangaea, too, once split apart along rifts like these. Each fracture in the crust, each pull of tension, is part of the cycle, the beginning of a new world, born from the slow motion of the Earth's plates. You rise again, tracing the Rift Valley from south to north, from the lush hills of Malawi to the steaming salt flats of afar. The land is split, yes, but it is alive, full of light, of warmth, of memory. Here, where the earth is breaking, something new is forming. And now, as the African continent continues its quiet transformation, you turn your attention to a different ocean, one that did not always exist, but slowly opened between friends now far apart. It is time to visit the Atlantic and watch its slow birth unfold. The earth turns beneath you once more, and now you drift westward across the shimmering surface of a familiar ocean, the Atlantic. Its vastness stretches from the icy shores of Greenland to the warm coasts of Brazil, from the cliffs of Portugal to the beaches of West Africa. But there was a time when this ocean did not exist. A time when the lands it now separates were joined together in a single sweep of rock and forest and desert, part of the mighty supercontinent Pangaea. The Atlantic's birth was not sudden. It began with a quiet crack, a subtle pulling of the crust deep beneath the soil and trees. That rift, unnoticed by the ancient creatures that walked the land above it, would grow into a world-spanning ocean. You return to the late Triassic period, more than 200 million years ago. Below you lies a unified landscape, what will one day become North and South America, Europe, and Africa, locked together along a seam that stretches thousands of kilometers from north to south. But deep beneath what is now Eastern North America and Northwestern Africa, a rising mantle plume begins to heat and weaken the crust. You float above the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. For thousands of years, lava floods pour across the land. Volcanoes erupt in fire and ash. The surface splits, fractures, and sinks. With each new eruption, with each new seam torn open, the plates begin to pull away from one another. The process is slow, perhaps only a few millimeters per year, but steady. A rift valley forms, stretching between what will become the eastern seaboard of North America and the western edge of Africa. This is the first breath of the Atlantic. Water soon begins to trickle into the rift, forming narrow, shallow seas. With time, these fill, widen, and deepen. Sediments are carried in by rivers, covering the volcanic rock in layers of sand and silt. As the plates continue to move apart, a mid-ocean ridge forms, a rising seam of volcanic activity where new ocean crust is created from molten rock. You glide along this seam now, the Mid-Atlantic Ridge. It runs like a spine down the center of the Atlantic Ocean, from the Arctic Ocean in the north to the Southern Ocean in the south. Along this ridge, magma from the mantle wells up, cools, and hardens into basalt. This is where the seafloor is born. You follow the process. As new crust forms, it pushes older crust outward, away from the ridge. The ocean floor spreads. The continents drift. Each year, the Atlantic grows wider. By only a few centimeters, yet over millions of years, that distance becomes thousands of kilometers. Even today, you can see evidence of this expansion. Along the coasts of South America and Africa, the shapes still match like puzzle pieces. The continental shelves, shallow areas just offshore, align even more closely. Fossils of the same species, including ancient ferns and reptiles, are found on both sides of the ocean. These are remnants of a time when the Atlantic had not yet opened. You drift higher, looking down on Iceland, a unique island perched directly atop the Mid-Atlantic Ridge. Here you can see the rift with your own eyes. In places, the Eurasian plate and the North American plate are visibly pulling away from one another, creating fissures in the ground. Volcanic activity is frequent, and the island continues to grow, built by the same forces that created the Atlantic itself. Back along the ridge, the ocean floor is marked by long fracture zones, scars where the crust is offset, stepping like broken tiles. These faults relieve the tension caused by uneven spreading, and are part of the ocean's hidden architecture. You glide now above Greenland, which once sat nestled against Europe. As the Atlantic spread, Greenland was pulled away and left to drift northward. You can still see the rocky scars along its coasts, places where the land split and separated from Norway and the British Isles. To the south, you fly above the South Atlantic, where the process unfolded in parallel. South America and Africa, once fused along their eastern and western margins, also began to separate. The split was clean and long-lasting, and over time, the South Atlantic filled with water. The ocean floor here is younger near the center, older at the edges, a symmetrical pattern formed by spreading. But the birth of the Atlantic changed more than just geography. The opening of a new ocean changed climate and currents. Before the Atlantic formed, Warm equatorial waters circled the globe, uninterrupted, through a single superocean. But as the continents drifted and new barriers formed, ocean circulation patterns shifted. New currents emerged, like the Gulf Stream, which now flows from the Caribbean up the east coast of North America and across the Atlantic toward Europe. This warm current plays a major role in regulating climate, keeping Western Europe milder than other regions at similar latitudes. You drift along the Gulf Stream, sensing the energy of the warm water as it moves across the Atlantic basin. It is a river within an ocean, carrying not only heat, but nutrients, weather, and life. As the ocean widened, it also became a pathway. In future millennia, humans would sail its waves carried by wind and current, forging new connections between continents, once joined by stone and split by time. But even before ships crossed it, the Atlantic shaped the ecosystems along its edges. Fish migrated across its vastness, whales followed ancient paths, birds flew from coast to coast. You look down upon the ocean floor, where sediments from both continents have gathered for millions of years. These layers contain the history of the ocean: pollen from ancient forests, volcanic ash from distant eruptions, tiny shells of microscopic organisms that once floated in surface waters. Scientists, millions of years later, will drill into these sediments to read Earth's story, studying magnetic patterns that show how the seafloor has spread, and discovering climate cycles written in mud and calcium. You pass now over the Sargasso Sea, a region of the Atlantic defined not by land but by currents. It is bordered by a great rotating gyre, the only sea without a coastline. Here the water is warm, calm, and filled with floating sargassum, golden brown seaweed that provides shelter for countless creatures. Even now, the Atlantic continues to grow. You float once again over the mid-Atlantic ridge, where magma still rises, where the Earth's crust is still being born. In the darkness below, hydrothermal vents billow black plumes of mineral-rich water. Around these vents, life thrives. Strange tube worms, blind crabs, and heat-loving microbes. This is one of the only places on Earth where life does not depend on sunlight, but on chemistry, feeding off the energy of the planet itself. You realize that the Atlantic is not done. It will continue to spread for millions of years. The continents along its margins will drift farther apart. But eventually, perhaps in 100 million years, the cycle may reverse. New subduction zones may form. The ocean may begin to close. And one day, the Atlantic may vanish, just as the Tethys Sea did before it. This is the Wilson cycle, the endless opening and closing of oceans as continents wander across the globe. The Atlantic is just one chapter in a much larger story. As you rise above the waves, gazing out across the horizon, you see not just water, but movement, memory, and time. The Atlantic may seem timeless and still, but beneath its surface lies the heartbeat of a world in motion. And now, as we look to the horizon, we begin to wonder, what comes next? Where are the continents heading? Could a new supercontinent already be taking shape? You float above the Earth, gazing down at the continents as they slowly drift across the surface like ancient, patient rafts. Over the past 4.5 billion years, the Earth has seen the birth and breakup of multiple supercontinents, vast landmasses made from the fusion of nearly all the world's continents. Now, as you look forward into deep time, you begin to wonder, what comes next? To answer this, you must first understand that continental movement follows a rhythm. Through the long history of the Earth, supercontinents have formed and broken apart in cycles. This process, known as the supercontinent cycle, plays out over hundreds of millions of years. It is not a single path, but a repeating journey. You look back first. Roughly 1.1 billion years ago, the supercontinent Rodinia gathered together most of Earth's landmasses. It was eventually torn apart. Later, around 600 million years ago, the pieces reassembled into Pangaea, only to break again. Then came Pangaea, about 335 million years ago, the most famous of the supercontinents, whose breakup gave us today's continents. Now we live in an intercontinental phase, with land masses spread across the globe. drifting apart or toward one another in subtle but measurable ways. You look down upon a world in motion. Africa is slowly moving northward, closing the Mediterranean Sea and pushing into Europe, forming mountains such as the Alps and Pyrenees. Australia is drifting steadily northeast, on a collision course with Southeast Asia. India, though already collided with Asia, continues to press northward, lifting the Himalayas higher. South America continues its slow westward push, squeezing the Andes Mountains as it overrides the Nazca Plate. North America drifts west, inching closer to the Pacific Plate. Antarctica, largely isolated now, continues to revolve slowly around the South Pole. Even the Atlantic Ocean, which once was narrow, is still widening along its mid-Atlantic ridge. But eventually, that will stop. You begin to imagine the future. Geologists and geophysicists have used plate motion models, simulations, and geological patterns to predict possible futures for Earth. Several scenarios have been proposed for the next supercontinent, each with its own name and unique vision. The first you visit is called Novo Pangaea. In this scenario, the Atlantic Ocean continues to open, while the Pacific Ocean continues to shrink. The continents that once formed Pangaea slowly drift back together, but in a new configuration. You watch as North America and South America rotate westward. The Americas eventually collide with Asia, closing the Pacific. Australia, now joined to Southeast Asia, merges into this growing landmass. Antarctica, too, moves north, locking into the underside of the continent. Novo Pangaea becomes a supercontinent straddling much of the equator, ringed by high mountains and vast inland seas. The Pacific becomes a memory, a vanished ocean swallowed by subduction. Next, you visit a different possibility, Amasia. Here, the focus is on the northern hemisphere. You watch as North America and Asia slowly drift together over the North Pole. In this model, the Arctic Ocean disappears, and a new continent forms that spans the top of the globe. The southern continents remain more scattered. This supercontinent would have massive polar ice caps, long winters, and deep interior deserts. The equator would be dominated by ocean, with climate patterns vastly different from today. A third scenario unfolds before you, Pangaea Proxima, a name meaning the next Pangaea. In this model, the Atlantic Ocean stops opening and begins to close. Subduction zones develop along the east coasts of North and South America. Over millions of years, the Americas drift back eastward, closing the Atlantic and colliding once again with Europe and Africa. You hover above a massive, nearly circular supercontinent centered where Pangaea once stood. The Mediterranean, Caribbean, and Atlantic Oceans all vanish. New mountain ranges rise as continents collide once more. You fly slowly across this imagined land. Broad plains stretching across what was once ocean. Towering ranges formed from crustal collisions, and new fault zones pulsing with energy. Finally, you explore the most radical future, a supercontinent known as Orica. In this version, the current motion of tectonic plates rearranges dramatically. A vast intraoceanic supercontinent forms, one not centered on former collision zones but in the middle of the oceans themselves. Here, continents break in unexpected places and reassemble in unfamiliar shapes. As you pass over Orica, you see a world that feels both alien and strangely familiar. Rainforests thrive in places once frozen. Deserts spread across lands that today are underwater. The Earth, ever evolving, has written a new chapter, one shaped by both its internal rhythms and a bit of tectonic unpredictability. In each of these possible futures, life is affected profoundly. When continents come together, inland areas become drier. Rainfall patterns shift, ocean circulation is disrupted. Species migrate, evolve, or vanish. Supercontinents often lead to mass extinctions, followed by bursts of evolutionary innovation. It has happened before. It will happen again. And in every scenario, one constant remains. The plates are moving. The Earth is not still. It is not finished. The continents you know today are merely a phase, a moment in a long, wandering journey across billions of years. You hover above the present-day Earth again, viewing the patchwork of land and sea. Somewhere in this drifting jigsaw, the seeds of the next supercontinent are quietly forming. We will not see it in our lifetimes, nor will our descendants. But in 200 to 300 million years, the land will come together once more, and the face of the Earth will be changed forever. Before you move on, you look one last time at the motion beneath your feet. Silent, certain, and immense. And now, with a full circle nearly drawn, let us visit the minds who uncovered this truth, the scientists who followed the clues in rock and sea and revealed the secret of drifting continents. You now rise above the Earth one more time, this time not to watch the continents move, but to follow the minds who first realized that they could. For while the planet has been reshaping itself for billions of years, the understanding of continental drift is a surprisingly recent discovery, and the path to uncovering it was long, uncertain, and filled with wonder. It all begins with observation. You drift back to the early 20th century, when maps of the world had become more detailed than ever before. From high above, the shapes of South America and Africa catch your eye, and the eyes of many before you. They seem to fit together, like puzzle pieces once joined and now gently pulled apart. Others had noticed this too, but one man in particular began to ask a bigger question. What if the continents really did move? His name was Alfred Wegener, a German meteorologist and polar explorer. In 1912, he proposed a bold idea, that all the continents were once joined in a single supercontinent, which he called Pangaea. Over time, he said, the continents had drifted to their current positions. You watch as Wegener presents his theory to a skeptical scientific world. He gathers evidence from fossils, identical species of ancient plants and animals found on now distant continents. For example, the Mesosaurus, a freshwater reptile, left fossils in both Brazil and South Africa. How could this creature have crossed an ocean it could not survive in? You see him point to rock layers and mountain ranges that match perfectly across continents. The Appalachian Mountains in North America align with the Scottish Highlands. Geological structures, coal beds, and even glacial striations tell a story of unity, land once shared. And yet, most scientists reject Wegener's theory. Why? Because he could not explain how the continents move. At the time, the Earth's crust was believed to be fixed and solid. The idea of massive land masses sliding across the globe seemed impossible. Without a known mechanism, Wegener's theory remained speculative. He died in 1930, never knowing that his ideas would one day transform geology. You drift forward in time now, into the mid-20th century, and deep beneath the sea. It is here, hidden under the ocean waves, that the next chapter begins. During and after World War II, scientists and navies began mapping the seafloor in unprecedented detail. What they found was astonishing. The ocean floor was not flat, but laced with mountain ranges, deep trenches, and vast plains. You float above the mid-Atlantic ridge, where the seafloor rises in a long, continuous mountain chain. This was no ordinary ridge. It was active, marked by earthquakes and volcanic eruptions. And it seemed to mirror a ridge found on the Pacific floor and elsewhere. Scientists like Harry Hess and Robert Dietz proposed a new theory, seafloor spreading. They suggested that new crust is created at mid-ocean ridges, where molten rock rises from the mantle and solidifies. As new crust forms, it pushes older crust away, causing the seafloor, and thus the continents, to move. This was the missing mechanism. Now Wegener's drift made sense. The continents were not plowing through oceanic crust. They were part of large solid plates which floated atop the slowly convecting mantle. This was the birth of the theory of plate tectonics. You observe another breakthrough in the 1960s, the discovery of magnetic striping on the ocean floor. As molten lava cooled at mid-ocean ridges, it recorded Earth's magnetic field, which reverses every few 100,000 years. These magnetic bands formed symmetrical patterns on either side of ridges, confirming that the seafloor was indeed spreading outward. Additional evidence came from earthquakes and volcanoes, which occur most frequently along plate boundaries. You drift above the Ring of Fire, circling the Pacific, where subduction zones and faults release immense geological energy. These zones perfectly matched the edges of tectonic plates, reinforcing the theory. You now watch as the global scientific community begins to accept what had once been dismissed. By the late 1960s, the plate tectonic theory had become the new foundation of geology. Continents do move, and more than that, they reshape the entire surface of the Earth. Today, scientists use GPS satellites to track the movement of plates with millimeter precision. You watch data stream from satellites in orbit to stations on the ground. The North American plate moves westward. The African plate creeps slowly northeast. The Pacific plate races across the ocean floor. What was once a theory is now measurable fact. You visit modern-day research vessels, drilling into the seafloor to retrieve core samples. These layers of sediment reveal millions of years of history. Climate change, volcanic eruptions, magnetic reversals, all written in rock. You step inside laboratories where geophysicists simulate mantle convection, building models of the Earth's interior using physics and computer algorithms. The mantle, once a mystery, is now mapped using seismic waves, vibrations from earthquakes that reveal the shape and behavior of the planet's deep interior. You even glimpse the interior of the Earth, as scientists do, colored maps of hot spots, subduction zones, and plumes. You see slabs of oceanic crust descending deep into the mantle, and rising currents of heat pushing the plates apart. Plate tectonics is more than a geological theory. It is a unifying principle that connects everything from earthquakes and volcanoes to mountain building, ocean formation, and even the distribution of life. And yet, even now, mysteries remain. Why do some plates move faster than others? Why do subduction zones form in some places but not others? What causes the cycle of supercontinents to begin and end? Scientists continue to explore, to map, to model. The story of drifting continents is not over. It is still being written, 1 centimeter at a time. As you float above Earth once more, you realize how extraordinary it is that human curiosity uncovered such a slow, silent truth. We cannot see the continents move with our eyes, but we felt their effects, saw their patterns in the rocks, and traced their paths through fossils and seafloor. It took vision. It took time. It took generations of thinkers. But today we know the continents drift, the Earth breathes, and the surface we walk on is never still. Now, with this knowledge in hand, let us return to the Earth itself, to the present moment, and reflect on the eternal motion beneath our feet. You now rise gently above the Earth one final time, the sky around you soft with twilight. The continents lie beneath you like familiar shapes on an ancient canvas. Africa, Asia, the Americas, Australia, and the frozen realm of Antarctica. They seem still, timeless, immovable. But now, after all we've seen, you know the truth. The Earth is always in motion. The continents drift, the oceans shift, the crust bends, rises, sinks, and cracks. And though we may not feel it in our daily lives, the surface we live on is carried upon the shoulders of vast, slow-moving plates, powered by forces deep within the planet. You look down on North America, gliding slowly westward atop the North American plate. Beneath its eastern edge, the crust is old and thick, a remnant of ancient collisions long past. Along its western edge, the land buckles and jolts with the tension of modern-day plate interactions. To the west, the Pacific plate surges forward like a restless ocean beneath the crust. Its edges are ringed by subduction zones and faults, a perimeter of fire and change that stretches from New Zealand to Alaska. You drift across South America, its Andes Mountains still rising under pressure from the subducting Nazca plate. Volcanoes smolder quietly in the highlands, Earthquakes rumble beneath the forests and cities. Across the Atlantic, Africa pushes northward, pressing into Europe. In the future, this movement will close the Mediterranean and give birth to a new mountain range. For now, it continues in silence, day after day, year after year. You glide over Europe, where past collisions have built the Alps and Carpathians, over Asia, whose broad expanse stretches from the Himalayas to the steppes, all shifting gradually across geologic time. Far below, India is still on the move, its northern edge continuing to press into the Tibetan plateau, lifting the Himalayas ever higher. You pause over Australia, drifting northeastward. One day, it will collide with Southeast Asia, transforming coastlines and raising mountains where there are now seas. You turn toward the South Pole. Antarctica, wrapped in ice, appears quiet, but even here, rifts are forming. Ice sheets shift, their weight pressing down on the crust. As glaciers melt and reform, the land below rebounds, flexes, breathes. The Earth moves in many ways, not only through the sliding of plates, but through the rebirth of rock. You descend now toward a subduction zone, where oceanic crust bends and sinks into the mantle. Here at the edges of continents, the Earth recycles itself. Rock that once formed the seafloor dives into the deep, melts and becomes magma. Some of it rises again to build mountains and volcanoes. The rest is transformed in the depths. You follow mantle convection currents, those deep looping rivers of rock that rise and fall within the planet's interior. Their flow is slow but unending. They drive the movement of plates. They sculpt the surface. They connect the deepest parts of the planet to the world we know above. Even in places without earthquakes or volcanoes, the Earth moves in other ways. You drift above Iceland, where two tectonic plates pull apart. You visit the East African Rift, where a continent slowly splits in two. You pass over the San Andreas Fault, where plates slide past each other, building tension until it is suddenly released. You float above the Mid-Atlantic Ridge, where new ocean floor forms continuously, like threads added to a loom, weaving the surface of the planet. And all across the world, from the deepest ocean trench to the highest mountain peak, you see the traces of a planet that never sleeps. Mountains crumble with time. Rivers cut valleys into the stone. Wind and rain wear cliffs down to sand. But even as the surface erodes, the forces below keep building, pushing land upward, pulling it apart, creating anew. You visit places where ancient collisions are remembered in folded rocks and tilted strata. Places where the very bones of the Earth tell stories millions of years old. Each hill, each cliff, each canyon is a page in the planet's book. You rise once more, higher this time, far enough to see the curve of the Earth against the dark of space. It seems peaceful, turning slowly in the blackness. Clouds swirl across its surface. The blue of oceans glows against the browns and greens of land. It looks serene, eternal. But beneath that calm surface, the Earth is alive. It is a living planet, not in the way we often think of life, but in motion, in transformation, in deep, patient change. The crust moves, the mantle flows. The plates dance across the surface like massive puzzle pieces that never stop shifting. This motion drives the cycle of oceans and mountains. It steers climate. It guides evolution. It creates and destroys. It has shaped our world and will continue to, long after we are gone. As you return from your journey, floating back toward familiar lands and seas, you carry with you a quiet understanding. The ground beneath your feet may feel still, but it is not. It is a traveler, moving slowly, endlessly, across the surface of a planet that is always becoming something new. The continents have wandered before. They are wandering still, and far in the future, they will once again come together to begin the cycle anew. The story of the Earth is one of motion, of drift, of transformation, and it never ends. Hello again, dear listener. You've just taken a journey through time unlike any other, floating above a living planet, watching its surface shift and change over hundreds of millions of years. From the mighty supercontinent of Pangaea to the slow drift of India into Asia, from the opening of vast oceans to the quiet rift valleys forming beneath our feet, you've seen how the Earth is always moving, always becoming something new. Continents are not fixed. Oceans are not eternal. Even the highest mountains were once buried deep, and the calmest plains once shook with fire. Yet all of this happens slowly, gently, at a pace far beyond human time. And while we may not feel it, we are all part of this great story. The land beneath your home was once somewhere else entirely, perhaps beneath an ancient ocean, or fused to a distant shore. The rocks in the ground may carry the memory of a mountain long since eroded, or the imprint of a sea that vanished before the first dinosaurs breathed. Earth's surface, like a vast, unending storybook, tells tales of collision and creation, of fire and ice, of motion and memory. As you rest now, let those stories linger. Picture the continents drifting quietly through time, the oceans opening and closing like gentle breaths. Imagine the rise of a mountain range where today there are none. Envision the calm heartbeat of a planet alive with motion. Deep beneath the surface, you are part of this ancient rhythm, connected to every rock, every current, every fold of land. You are standing on a world that is still becoming. So now, close your eyes. Let the slow music of the earth carry you. Let your thoughts drift like continents on a vast blue sphere. Let the stillness of the present wrap you like a warm blanket, even as the earth turns quietly beneath you. And as you drift into sleep, remember, the story of our world is always unfolding, even in dreams.